Hey guys, in this video I'm going to explain the second logic game of the December 2013 LSAT, which is PrepTest 71. This is the game involving job applicants being evaluated by human resource officers. This game was a little bit trickier than the first game of the section. This game I would consider a matching game because we're associating the candidates with the human resource officers. There's no ordering component here. Nothing is being placed in any kind of order or sequence. So I've laid out the rules here. I'll explain all of them. We have that G is evaluated by U. So I laid out the 4 human resource officers, and because we're assigning the candidates to the officers, and there's some ambiguity regarding how many candidates each of the officers will evaluate. So I chose to assign them this way based on the orientation of the rules. For example, the other ones, like the second one, that F and L have to go with the same officer, this can be represented with a vertical block right here. We know that neither H nor M can go with I, so those are vertical blocks with slashes through them. We know that K has to be alone. K cannot be with any other candidate in the same column. And then we know that there are going to be more people assigned to S than assigned to T, so I put that S is greater than T, and then I put down 2 spaces above, 2 spaces in the S column just to indicate that S will have at least 2 candidates assigned to them. So this is just a general setup, not too much in the way of upfront inferences here. We'll be doing more work over the course of the game. So let's start off now with question number 6, which is a general orientation question. We're simply going to take the 6, we're going to run through the answer choices one rule at a time, checking for violations. So we can start with the fact that K has to be alone. Any choice where K is with something else can automatically be eliminated. Scanning through the choices, we see that D has 3 people on S with 2 Ks with 2 others. That's unacceptable, so D can be eliminated. Let's use the rule that F and L must go together. Any choice where they do not go together can be eliminated. This gets rid of B. The others are good on that issue, so we'll keep moving. We know that I cannot be with either H or M. So scanning through the remaining choices for this, we see that C has I and H together. That's unacceptable, so C is gone. We're down to A and E now. We haven't checked the rule that G has to go on U, so let's look for that, and sure enough, E violates that, having G on R. So E is gone, leaving A as our answer for number 6. Next, number 7, if H goes to R, what could be true? So we start off by putting H down on R, and let's see what consequences result. Well, we've got to put K somewhere, and K has to be alone, so the only place that K could go would be on T. There's no other place for it to happen. So what variables do we have left? We have F, L, I, and M. And we know that I and M can't go together, and so we have to avoid that from happening. We have to make sure it doesn't happen. So where will we put F and L? F and L have to go together. If we put them together on R, for example, we're going to end up forced to put I and M on S, since we have to have 2 things on S. So, and same goes if we put F and L together on U. If we put them with G there, again, I and M will have to go to S. So we're going to actually have to put F and L on S, and then I and M will go somewhere else. We don't know exactly where, but F and L will definitely go on S. I and M are basically floating around. As long as we avoid having them in the same place, we'll be good. So we'll just run through the choices, checking what could be true. Could F go to R? No, F is going to S, so A is gone. Could I go to S? Yeah, actually, there's no reason that couldn't happen. There could be 3 things on S, remember. I could basically go anywhere right now, except on R, because H is there, and except on T, because K has to be alone. So B is our answer for 7. I will run through the other choices though. Looking at C, K on R, no K's on T, so C is gone. Looking at D, L on U, no L's on S, so that's gone. And looking at E, M on T, no. M cannot go on T because K has to be alone, so E is gone, leaving B for number 7. Next, number 8. If exactly 2 applications go to T, then each must be true except. So right away, if T gets 2, S is going to have to get 3 because S always has more than T. So then R and U will each have exactly 1. And since K has to be alone, K is going to have to go on R for certain. Now we know that I conflicts with both M and H, so we're going to have to avoid having I with those guys. And so I is going to, basically, since F and L have to be together, we could either put F and L on T or F and L on S. F and L on T would force I, M, H all together on S. So we're going to have F and L together on S along with I, and then have M and H going on T. That's the only way to comply with the rules. So everything ends up being fully determined, no ambiguity at all. We'll now just have to run through the choices. Must R get exactly 1? Yes, so A is gone. Must U get exactly 1? Yes, so B is gone. Must F go to T? No, F is actually going to S, so that's not a must, and therefore it's our answer. I will look at D and E though. I going to S? Yes, we see that right here. And finally E, L going to S, we see that as well, so C is our answer for number 8. Next, number 9. If M goes alone, what must be true? So you see I've drawn here basically M and K end up being interchangeable on R and T, since R and T are the only places that anyone could possibly be alone in this game. So the remaining, we don't know whether M goes to R or K goes to R, and same goes for T, but we know that those 2 columns are being occupied solely by K and M. The remaining, we have the variables F, L, I, and H. We know that F and L have to go together due to the second rule, and we know that I and H cannot go together due to the third rule. So we're going to have F and L with one of I or H in order to ensure that I and H don't end up together elsewhere. So we know that S has to have more than T, which is why I've already placed at least 2 spaces on S. So we can't put F and L on U, because if we did, then we'd have to have 4 things on U, and then we wouldn't be able to have 2 things on S, because remember there are only 7 variables. So we're going to have F and L on S for certain, and then we're going to have one of I or H on S. The other one of those 2 will have to be on U, and that's basically everything we can determine for this. So we'll just run through the choices, seeing what must be true. Must M go to T? No, as we said, M and K are basically interchangeable on R and S, so A is gone. Looking at B, L goes to S, that's a must as well. So now we'll run through the choices. Must M go to T? No, as we said, M and K are interchangeable on R and T, so A is gone. Looking at B, L goes to S, yes, that is a must. That's one of our inferences here, so B is our answer. I will run through the other choices though. K goes to T. No, K is interchangeable on R or T. We don't know where it's going. Looking at D, I goes to S. No, I and H are interchangeable on S and U, so that's gone. And finally E, H goes to S. No, H could go to either S or U. We don't know, so B is our answer for number 9. Next, number 10. If F goes with I. So that creates a vertical block of 3 variables, F, L, and I, since F and L have to go together. And so you want to think about where F, L, and I could potentially go. And looking at this, it appears that they could go, either on R or S potentially. S maybe seems a little bit better. The one place they can't go is on U, because that would be 4 variables all on U, and then we'd only have 3 to allocate among the remaining 4 spaces. And scanning through the choices, sure enough, we see that in choice C, L goes to U is something that we know cannot be the case. That's a cannot. So C is actually our answer for number 10, and we don't really have to draw anything at all for this question. Finally, number 11, if F goes to R, how many of the other applicants can we determine? Well, if F goes to R, we know right away that L has to go to R also because F and L are always together. So right away we've got, aside from F, we have L, K, and G all placed. K has to go to T because it has to be alone. So our remaining variables are M, H, and I. Now, we know that neither M nor H could possibly be with I, so if we were to put I on S, we're not going to be able to put either M or H to fill the remaining space. So therefore, I will have to go somewhere else, and M and H will have to fill those spaces on S. So aside from F, we can count 5 other variables, L, M, H, K, G, that we are able to determine. So the answer to this question is E, 5.